Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a great pleasure to introduce this afternoon IBM fellow Grady Booch. Of course, many of you know Grady's work, familiar with it. He's been devoting his life to the development of software and object-oriented design and analysis. He was the chief scientist at Rational from its beginning, Rational Software Corporation from its founding in 1981. And he continues to be the chief scientist through the acquisition of Rational by IBM. Grady, of course, has done many, many different things in the object-oriented community, the software design community. But one of the great contributions is his work as a original author of the Unified Modeling Language (UML), and of course the many books that he's written. Many of us, I'm sure, are familiar with the seminal object-oriented analysis with applications that he wrote, and he's also written the UML User's Guide and many, many papers. So this afternoon, Grady's going to be talking about the promise, limits, the beauty of software. Grady's been working in this field so many years. He's got many deep insights, and I'm very happy that he's going to share them with us today. So please welcome Grady Booch.
So I guess the first thing I need to say is my comments are mine, not necessarily that of IBM or anybody living or dead or those kinds of things. Because if you think about it, it's kind of strange. Here I am, an IBMer amidst you, using actually a Macintosh, but that's another story. I mostly do that to annoy the hell out of IBM management. I think they made me a fellow largely because I'm unmanageable. And as a fellow, there are basically three things I'm doing these days. The nice thing about being what I do in the company is that I have lots of degrees of freedom to pursue what I find interesting for the company. And the primary two things that I'm spending time on are in the area of software architecture. The next book I'm working on is a handbook of software architecture. Some of you may have visited my website, where my intent is to take a look at 100 different seminal systems around the world and simply document their architecture. If you're a civil engineer, you learn by studying the works of great other civil engineers and designers and architects. And in software, however, we have no such reference. And therefore, most people learn their systems because of simply discovering it through tribal memory. They'll work up in a particular area, they'll study it for a while, they'll grow up inside it, but often have no insights into other ways to design systems. So I'm looking at everything from, in fact, latest archaeological digs have been for the NASA's JPL Pathfinder, been spending time with the London Underground folks, Symbian, the operating system for cell phones, and later today, the primary reason here I'm on the campus is to spend a little bit of time with the Word team, because I'd like to document their architecture insofar as they'll let me to do so. I spent time in the past few months with the folks at Photoshop team, eBay, Amazon, you name it, it's sort of across the board. And I've learned some things along the way. Indeed, that's why I write books, primarily to learn. There's so much I know I don't know right now. The second thing where I'm spending a lot of my time is in the area of collaboration. So if you happen to be in Second Life, go visit me as Aleem Theus, that's my avatar name, where we're doing some research in the areas of what can one do in virtual worlds to support temporal and geographically distributed development. We think there are some interesting opportunities there. So those two areas are the primary places where I'm spending my time. The third that's worthy of mentioning here is that in Rational, I work with our CTO, a guy named Martin Alley, to manage our research program with IBM Research in Watson in China and India and other places. So we actually had some interesting discussions this morning on some interesting things you guys are up to, and shared a little bit about some of the things we're up to as well. And if you think about it, you know, we all are doing some common things here. We're all trying to fight the evils in the world of complexity and apathy and Google and all the other... Did I say that? Yes, I did. Not necessarily saying they're evil, but they're certainly a worthy opponent in this marketplace. And that's a good thing. We like having opponents that are worthy of fighting, and helps make us all better, I think. So earlier this year, I was invited by the British Computer Society to give a lecture, the Turing Lecture in England, not the Turing Award, but this is the Turing Lecture named after, of course, Alan Turing himself from the University of Manchester. And basically, it was taking a look at what do I see happening in the world of software in the coming decades. My focus inside Rational, and it continues to be inside IBM Rational, and for the software group, is worrying about the next 5 to 10 years. And so that's why I'm doing the two things I'm doing, as well as a variety of other activities that make me look out into what's possible. So in the hour or so we have here, I'm going to talk for a while. We'll have time for questions at the end. Along the way, if you have any questions or if I say something that offends you or makes you stand up and want to throw things at me, go ahead and ask me questions then, and we'll try to address it at that point. But I'd take a look at what I have learned over spending time with thousands of projects. What makes it difficult for us to take our notion of a vision and turn that into naked running code? These are the limits of software. And yet at the same time, there's so much that we think we can do with software. We're going to look beyond how we're limited and also take a look at what software might do for us. But then there's a third aspect, and this comes about primarily because of the work I've done on the architecture side as well as the academic community. It's the issues of how do I demonstrate the beauty of the software we have produced. We have created artifacts as a community of incredible complexity, and yet how do we share the beauty we have therein so we can inspire the generations after us to go off and build these kinds of things as well? Too many times I've had colleagues come up to me and say, I would never want to have my son or daughter or dog or cat go into the software field. It's just a terrible place to be because it's going to be outsourced. There's no fun in it anymore. All the cool stuff's done. And I just want to throttle them by the neck and say, well, no, this is not so. There is still lots of really cool things to be done here. There are lots of opportunities for innovation. Innovation will never be outsourced. And there are lots of opportunity to craft truly wonderful things in the things we produce. Among other things, I spend time with the Computer History Museum in the Bay Area, and a few years ago I went to their board of trustees and convinced them that they should also become a museum of software, not just hardware. It's fun to look at the old bits of hardware, and that's really interesting. But if you think about the trajectory of things, the next generation of people who are going to look at hardware, well, they're going to need to have microscopes to basically look at the hardware because it's going to be uninteresting. And so they need to make a shift to what I think is the real fundamental value of our industry, which is not just the machines upon which these run. These are commodities largely, but now rather the software that we have created as an industry. And so we're trying to preserve things such as the early Fortran compilers, some of the, not just the languages, but also some of the early applications. We tracked down, for example, the source code to MacPaint, which it's a beautiful piece of code. It truly is. Apple has not let us release it to the world because obviously it's so important to the bottom line of Apple, and it would destroy their shareholder value if we released it. But I've looked at it, and it's a beautiful piece of code. I've been doing similar things with other companies, and indeed, wherever I can here, I'm urging the Microsofties to say, go save the source code to Word and to Windows and all these things, because 100 years from now, Bill's not going to care. Your lawyers might, but Bill's not going to care. And you'd certainly want to preserve this stuff for future generations. It would be a shame if you as a company had basically let all that stuff evaporate. So, think about putting that in a public escrow or something so that we can get to it eventually. As I was trying to track down the source code for the IBM 360 operating system, I was amused to discover that IBM has lost a copy of it. So IBM itself no longer has the source. So I'm going to academic places and see if we can track it down. So anyway, that's what keeps me busy. As Bjarne Stroustrup has observed, our civilization runs on software, but he's an insider, and so he's going to give us a little bit skewed view of what software offers for us. Let's look at somebody radically different, in particular the former president of Poland, I guess it was? Yeah, and which he observed. This is upon his first visit to Western Europe, where he said, you guys have so much. Why can't you use your computers and other things for the search for love? Now, he's not talking about Match.com or something like this. But I think what he was pointing out is that in the end, the value of what we do as a community can be measured insofar as it touches the human spirit. So it's rare you're going to find a technical lecture in which one of the first things that comes out of your lecturer's mouth is about the importance or the relationship of software and love and software and beauty. But indeed it is there. The things we have created are wonderfully complex. They're incredible creations. And yet, in the end, insofar as they change the way the world works, that's, I think, ultimately where its value is. And what he's pointing out is there's so much more that can be done. To that end, I would observe that there are great things that we know that software has done for us. And this is why it's such a privilege to be a software developer. They can amplify human intelligence. They can fuse, coordinate, classify, analyze information. But at the same time, we know there are limits because we know that software-intensive systems can't replace human judgment. About a year or so ago, I was approached by some of the folks at Homeland Security, and they said, we've got this really cool idea. We know that, first, you know, that's a warning flag. Oh, a government official with a cool idea. My BS meter pegged. So they pointed out that in the government we've got all these silos. We've got Social Security information and tax records and all these retirement kind of things. And what they wanted to do was to go searching across them, looking for patterns of really bad behavior. So in the end, they literally said, we'd like to cut across them, find the bad guys, and automatically produce a warrant for their arrest. Now, I politely suggested that what they would wish to do may be technically feasible, but I had a few problems in terms of violation of my rights as a human being for so doing. And so we know that there are some things that we can do that we probably shouldn't do because these are systems for which the presence of human judgment is certainly still a very valuable thing. We also know that there are limits in the sense that we can't create new semantics, we can't create new knowledge. We can look at it in different ways, perhaps through our automated systems, but ultimately there are some things that our software systems cannot do as well as should not do. So to put it another way, not everything we want to build can be built. There are some fundamental limits, and it's also the case that not everything we want to build perhaps should be built. And these are the more social and moral kinds of limits. It is also the case that, as I alluded to, there's still tremendous opportunity for exposing the beauty in our software systems. Dick Gabriel has written some delightful papers to this end. His Less is More paper, I think that's the title of it, or Good Enough Software is basically his theme, is saying that, you know, sometimes in our field we search for absolute precision and perfection, but there is no such thing. But rather what we should search for is elegance and beauty and simplicity, because we know when we've gotten to that point we probably produce something that's very real and valuable. Buckminster Fuller, the architect, has often observed, or had often observed, that he doesn't worry about beauty in building buildings, but he knows that when he is done, if the thing he's created is not beautiful, then he's failed. And yet it's a very difficult thing to measure. How do we in software measure beauty? Well, we do it through simplicity and elegance and cleverness, but it's difficult to get a true handle upon what that thing is. I guess the conundrum with this, however, is that while we are building things with incredible complexity, most of the world doesn't see it at all. So a little bit of a guessing game here. How many lines of code do you think were written in the world last year? And we'll include Visual Basic in that count. But take a wag. A trillion? Actually a little too high. 1 billion? A little too low, so now you can apply a binary search algorithm to the problem. 10 billion? 10 billion, a little bit low. It's about 33 billion according to my back-of-the-envelope calculation. How do I get that? Well, there are about 15 million software professionals worldwide. Surprisingly, as I discovered when I came into IBM, not every manager codes. Wow, what a shock. So, of course, all of you do here, right? All the managers code. So back of the envelope calculation says, maybe 20 to 30% of those professionals actually cut code for a living. And of those people that cut code, on the average, it's somewhere around 5 to 10,000 lines of debugged code per person per year. That's also an average. Looks kind of small, but remember, we're looking at an average. We know that the bell curve is skewed, that there are people who just do outrageously amazing things, and you want to treat these people really well and pay them lots of money or do whatever it is to keep them around. Multiply those together and you get around 33 billion lines of neuromodified code per year. But if you cumulatively add it up over the years since about 45 or so, when the first high-order programming languages truly began to emerge, it brings us to about 1 trillion lines of code. And so 1 trillion lines of code that we as an industry have built over the years, that's an amazing number which represents the output of a very vibrant community. And it's that 1 trillion lines of code that we have used to change the world, change the way that people work in the world, the way that civilizations interact with one another. That's tremendous leverage from that kind of source code. And yet, as the average person will realize, we desire to make that code and all the software utterly invisible. Insofar as the bones of our implementation stick through, we've actually failed, because for the average user, it should be seamless. An eBay story here. eBay's got most of their stuff, all their servers sort of living in one space on the West Coast. They're desiring now to split things across to Europe and Asia. And yet for the average user of eBay, which is, think your grandmother, that's sort of the average user of eBay, they could care less about all the stuff that's below the surface. And they have an assumption of a particular behavior that eBay offers now. They post something for sale, they go to another page, and poof, it's there automatically, immediately. And yet, if you start figuring out how to divide things up across literally the globe, then getting that same kind of quick behavior is not so easy. So one of the difficulties for them is, how do you give the illusion of simplicity in the face of incredible complexity below the surface, so that your grandmother types are actually hidden from all this kind of stuff? That's a real challenge for them. And it's something we all strive to do, of course. That conundrum leads me to observe that in our world there are a number of other conundrums that we have to face. Now, this is going to diverge into an area that we often don't think about as developers. I mean, you guys are hardcore researchers, you're down there in the bits, you're exploring some very fascinating things, but ultimately I want to urge you to pop your head up every now and then and realize that the things we do have ethical and moral implications to them. For example, we know that the presence of the web has utterly changed the way that individuals collaborate and businesses work with one another. And yet at the same time, this has created an environment where terrorists, other folks, can work together unimpeded. In Second Life, for example, I've heard stories that some of the government's intelligence agencies are really worried about things like virtual worlds, because nowadays you find a spy, he or she drops some stuff in a physical site to exchange information. Well, the web's made it a little bit more difficult to track these folks down, but now imagine I have a virtual world where somebody from some other part of the world can log in as some anonymous character, actually drop some information someplace in the virtual world so that some other bad guy or bad woman can pick it up. How do you protect against that? And the answer is, well, you can't. I'm not sure you even should. But nonetheless, it creates all sorts of dilemmas for folks that care about such a things. They've worried, in effect, of the changing nature of war not just being in the physical way, but truly cyber kind of warfare. It's also the case the web has provided unprecedented mechanisms for social networking. This gives me the opportunity to show Britney Spears' MySpace page. At least this is the excuse I gave my wife when I was cutting and pasting this page. But at the same time, the web also creates an incredible place for the exploitation of children and fraud and other theft that how do you protect against? It's also the case that software-intensive systems permit real-time and distributed access to information. I've got here a little picture of just a weather station. You can just buy this thing off the shelf, kind of plug it in, and all of a sudden I now make the local weather available to anywhere in the world. And yet at the same time, they can erode personal privacy. I gave this first when I was in London, and it was particularly poignant because London, of all the cities in the world, is the one that has the highest concentration of cameras throughout the city than any other place. And there's a tremendous amount of money that the UK government is spending on facial recognition. So, and the end game is, well, gee, wouldn't it be interesting if I can identify a bad person, however I may characterize bad, I find them in a certain place, and even though, you know, they're not necessarily doing anything wrong, I can track them wherever they might go, and I have the technology to do this. Can I do so? Is it a good thing? Is it a bad thing? Well, how do you weigh off the rights of the individual for the rights of all? Hard to say. It's also the case that email and other mechanisms have changed the velocity of information, and yet there's a downside to this as well. Historians tell me that this is threatening our preservation of history. There's a lot of work that DARPA is doing right now in terms of preservation of, or rather the digitization of a lot of government records. We had the missing 9 minutes during Nixon's era, and now we have the missing emails during the current administration. Email doesn't just disappear, you know. It truly doesn't. It may be hard to find, but it just doesn't go away. And yet, if you look at historians who have surveyed, you know, the last multiple decades and the centuries before that, there have been lots of written artifacts that we can go back to and say, well, this is sort of what life was like. This is what this person's life was like. How do we do this now if I'm 2 or 3 generations hence, and all of a sudden we have no way to look at a JPEG format because we've invalidated that format? This is one of the things the Computer History Museum is trying to preserve, the ability to read formats for lots of things. There are tapes upon tapes of data that NASA has for early missions, and these things are not only eroding physically, but we often have no machines to read those tapes anymore, nor do we have the protocols for even decoding what those files are. And it may seem funny now, but and I know the folks in Massachusetts have been worried about this, will .doc formats be available, you know, 1,000 years from now? Will we be able to read these kinds of things? And historians worry about this kind of stuff. It's also the case that software-intensive systems have created new forms of artistic expression. I've got here a snapshot of a synthesizer, just a pure software synthesizer. Of course, the downside of it is multifold. We have enabled, through software-intensive systems, to allow musicians with absolutely no talent whatsoever to make lots of money. And this reminds me of Britney again, but let's not talk about her. And yet at the same time, this is of course what's utterly annoying most of the major media companies right now. They simply don't know how to deal with this kind of stuff. And of course this is in the midst of all the news. How do you weigh these off? It's also the case that software-intensive systems have enabled and accelerated scientific research. That's cool. I've had some interesting conversations with Dr. Craig Venter, the gentleman who, in parallel in competition with the National Institute of Health, decoded the human genome. And yet, at the same time, there's some amazing things happening because of software-intensive systems in the medical fields. It's also the case that through software, we're now able to build weapons that kill people a lot faster than they used to, and kill more people along the way through software-intensive things. The work of the Army's future combat system to really sort of bring every individual soldier to be an IP node. There are some amazing things you can do if you make that happen. Imagine hacking a soldier. Wow. It's also the case that software is certainly a part of the very fabric of our civilization. And insofar as it is weaving its way into the dark spaces and becoming more and more invisible to others, the problem is that the complexity of what we're building is growing exponentially. And so our ability as an industry to just keep our arms around all the stuff we're doing and to deal with the potential interactions of systems over which we have no control of some of those systems, it's absolutely frightening. I've done archaeological digs of the northeastern power grid, and it's really very scary if you think about it, because many of the folks who run the power grid really throughout the whole country are doing with systems that are very, very fragile indeed. This is not only just the power generation, but also the power transmission. And it's not just the security of these systems. And you can find easily, if you look a little bit hard, to see a number of unsecured devices of those networks. What if somebody were to get in and sort of bring down New York City? This would not be a good thing. But also it's the problem of how these things work together with one another. They're very chaotic systems, they're very fragile, loosely coupled systems, and yet no one has really planned them across the grid for the entire United States. And so the fact that they work as well as they do is owing to a lot of good luck, for one, and the fact that these systems are so resilient. But as we begin to draw more and more from them, then the opportunity for these systems to fail in catastrophic ways because of software problems underneath them increases exponentially. And of course, if that happens, and lawyers get involved, and then all the fun gets sucked out of the air for us. There are no lawyers here? I don't know if you have any lawyers on your research staff. I mean, the whole issue of copyright law is just a fascinating one. Wow, don't get me started on that one. In preparation for this work for the British Computer Society, I went back and took a look at Alan Turing's life himself, and he truly was an enigma, to use the name of his biography. He was just an amazing fellow. He observed that in terms of what he saw the future of software to be. And remember, he was a mathematician. He sort of did so many different things. But this is about 50 years ago, and so what he was saying then is kind of the present now. He was observing this notion of what today we would call the Turing test. Now, he never called it the Turing test. It was actually named that by Clark in 2001: A Space Odyssey. So that's where it came from, and the whole thing about HAL. So Turing was pointing out something that was an old Victorian game, a game in which you would put people in two different rooms and you communicate with them via letters or whatever, and the idea of the parlor game was to figure out, is this person a man or a woman? And he extended to then say, well, can I do that same kind of thing in not just a man or a woman, but also a computer? And his prediction was that we'd be able to do that in about 50 years. A funny story about him, too, that he apparently was telling this story to somebody inside AT&T, or Bell Labs at the time. He was in the Bell Labs laboratory, and somebody asked him about this, and he said, oh, I don't mean to simulate a great intelligence, a genius. I just want to simulate a mediocre mind, someone like the president of AT&T. And there's deathly silence. So here we are, simulating the intelligence of the mediocre mind. Well, enough about George Bush, but that's me again, not IBM. Don't worry. He also observed that there are indeed limits, and his limits that he saw primarily came from his mathematical foundations. He realized this notion of computability, which said that, well, if it's not computable, then it's something that we're not going to be able to do in software. So that's the ultimate limit for him. And yet, as I look at the problem, I think that's maybe the fundamental limit, but there are lots of other things that make it difficult for us to take our vision and turn that into reality. Turing also observed the beauty in software, and he saw it from a mathematical perspective. Again, being a mathematician, he was very concerned about elegance and simplicity, and that's how he saw beauty in the software systems. And yet realized he was dealing with software systems that by today's standards, somebody in high school would whip out quickly. They were relatively small systems, a few hundred, if not a few thousand lines of code, and he had never begun to experience the problems of scale that we ourselves face today. There was a contradiction in his life as well, too. Turing, of course, was the man behind the breaking of the Enigma code, the German telecommunications code that was used for a lot of their naval work. There were some poignant stories in that regard, and that his team had actually broken the Enigma code fairly early on, and yet to expose the fact would have meant that the Germans probably would have changed the code, and that would have caused devastating things. So there are a number of circumstances where they'd gotten in messages from naval broadcasts. They knew that an attack was going to happen upon a particular convoy, and they actually did nothing about it, because to do so would expose the code, and at the same time hundreds of people were killed. So difficult thing for him to deal with. And so really his work shortened the war effort by a couple of people saying, well, not a couple, a number of historians by several years. And yet at the same time, later in his life, Turing was actually condemned by the very country that he saved, Turing was a homosexual, and that wasn't exactly something that you did in Victorian England or turn of the century England and through the war. He eventually was found out, if you will, and chemically castrated, and he eventually got off the drugs and said enough of this and committed suicide. So his life was prematurely ended. So his life was very much a contradiction. A number of things that he did, he was so far ahead of his time in terms of the things that he had began to pursue. Issues of quantum computing, for example, far ahead of Feynman's work even. The notion of artificial life, all of these things. So, as I alluded to, he had really spent a lot of time, or at least from a mathematical perspective, trying to understand what we could and couldn't do. I've recast this in what I call the limits of software, saying, what are the things that make it difficult or impossible for us to take a vision and turn it into reality? You had a vision to build the next generation operating system. It didn't just happen overnight. It was painful and difficult and chaotic. What are the things, I would ask you, that made it difficult for you to turn that vision into reality? Let's walk through a few of these. For some domains, the laws of physics intrude. I was doing work with another defense-related project, and they said, okay, we've got this global kind of defense command and control system, and we want to have the synchronization of events around the world to a certain really precise number. And I said, well, that's really fascinating, but that won't happen in this universe. That it violates pretty much everything we know about the synchronicity of events. You just can't do it to that level of precision. Yes?
Given all the devices on one planet, cannot you get much more precise synchronization than the velocity of light?
You can, but the problem is they wanted to go beyond what the speed of light could even do for us. Even with, and you know, this is the government. They sort of ask for what they want. But they are asking for synchronization down to a very, very precise level that you simply could not get that accuracy around the world. So I was, and also the path they were on, the design, was just going to be so utterly expensive. I said, well, gee, you have this thing called the GPS system. Why don't you get a good enough answer and that'll do it for you? And they said, oh yeah, that may be okay. So this is an example of relaxing a particular constraint that is so overwhelming, no amount of code is going to deal with it. Just relaxing it a little bit will give you the opportunity to do some other simpler solutions. NASA has this problem. I was doing some work with one of their deep space probes, and Barry Bain tells a story because it happened to him a few decades ago, and by gosh, it happened to me about 3 years ago. They said, okay, here's the thing we're building, let's do a design review, this is cool, and by the way, we can only write so many lines of code because otherwise it will weigh too much. And I said, wait a minute. Way too much. They said, well, yes, it does, because X lines of C translate into Y bits of object code. Those Y bits of object code have to be blasted into a PROM, and there are only a certain number of space-qualified PROMs that exist in the world, and those PROMs have weight. Ergo, software has weight, and we can't exceed that. We also know, they told me, this is absolutely real, I'm not making this stuff up. They also said, well, remember that computation follows all the normal laws of thermodynamics, so when you compute, you cast off heat. And therefore, if I'm doing a deep calculation, I may cast off heat on my computer on board the spacecraft, and I may actually have to program my spacecraft to rotate when that happens so I can cool it off and it doesn't get too hot. So heat and weight are actually things that are limiting factors for these kinds of devices. Now, imagine if your Vista team had to worry about that. Ooh, this weighs too much. That'd be kind of scary. The one project I've been doing work with where people have to deal with relativistic effects are back to the GPS folks. The satellites are far enough away and they're moving quickly enough, they actually have to make adjustments in their software for the fact that there's dilation of time at that speed. Next level up deals with what I call the laws of software, and these are things that David Harrell has observed in his delightful book. You go to places like FedEx or UPS, and they'll tell you that mathematically we sort of know that if you have about 10-ish packages going to about 10 different cities, we can do a brute force calculation to tell you the optimal routing of all those packages. Problem is, in flight on any particular day, not including Thanksgiving and Christmas, where things go nuts, they have around around 15 million packages in flight to about 10,000 different destinations. That's not within the cities, but that's the major cities themselves. And there simply aren't enough seconds in the known universe to be able to calculate that, the optimal routing given the computational resources we have. So what do? Well, you do something different. You apply neural nets, you apply some genetic algorithms, you do some exotic things to get a good enough answer. The corollary to that is a problem of algorithmic breakthroughs, which some domains have to deal with. One I'll mention in particular is the computer graphics world in both games as well as films. So if you look at the history of algorithmic breakthroughs in computer graphics, the first thing we had to break through, Jim Blinn and crew kind of did this, was how do I draw a teapot? I mean, how do I make that happen? You've seen the classic teapots. The next thing was, how do I then make that teapot look like it did not come from a Barbie's set, i.e. something other than plastics, the problem of textures. The next thing was issues of reflection and just having, the contributions of all the things around you. So this is where all the ray tracing algorithms and cool stuff came into be. But then the next algorithmic breakthrough dealt with kinematics, where you want to have these things actually move about and make them look real. The next level of breakthrough dealt with problems of interesting textures like water in particular. That was really hard for people to do. Digital Domain, the company that did the special effects for the Titanic, they did the special effects for The Day After Tomorrow. They do the best water in the business. They've got some great algorithms. But prior to their breakthroughs, water looked just not like water at all, but now it looks pretty real. The next algorithmic breakthrough was the problem of clothing. There's this scene in Titanic where, if you look real close and look at it from a geeky perspective, but she's standing on the bridge with Leonardo, and they're doing their thing, I'm king of the world thing, and she's got a scarf, a red scarf. Apparently, the CEO at Digital Domain told me John Cameron thought it looked horrible. It was a real scarf. It didn't wave right, he said. So I said, okay. So they digitally removed her red scarf and then put in a computer graphics one, which of course cost them lots and lots of money to do so. But it led them down the path of building algorithms for clothing, where you really had to build some really incredible models for the clothing itself and how does it interact with bodies, how does it deal with different kind of textures. And there have been algorithmic breakthroughs to deal with that. The problem people are dealing with now is kind of represented here. I am a Halo freak, by the way. So I am so waiting for this to come out. But here's a little clip from it. And I want you to take a look at what you don't see in this.
I know you.
This just gives me my Halo rush.
Your future.
And what you don't see, I mean, it's amazingly photorealistic, but you don't see faces. And so what this is pointing out is where this community next needs to go are algorithms for mostly human faces, because we as humans have seen other humans for a few millennium or 6,000 years if you happen to be a creationist, depending upon whatever it is. But we have all these cues that we know that we've seen, and we don't quite have it right. So this is the next level of algorithmic breakthrough that we know we need to go to. Once we get there, then you don't need actors and actresses, or maybe you need them once, but oh, stop that. Okay, there we go. There we go. A corollary to this is the problem of concurrency. We talked about this a little bit earlier this afternoon. I've gone to a variety of gaming companies, and they've showed me some fantastic things they're doing with the cell processor, which of course is the basis of the next generation of most of the next consoles. So you've got here an 8-way asymmetric processor, or set of processors, and yet I'd say not most, but just about everybody doesn't know how to program these things. We can do it in brute force ways to say, well, audio works on this chip, and video on this one, and we do AI on this one, but it turns out to leave the cell as a whole underutilized. So we know that there's more that can be done, and yet we haven't had a lot of good breakthroughs in how one does concurrency at an intimate level. And this is going to be a very real problem. And we're spending time on it. I hope you guys are spending time on it, because this is the nature of the next generation of platforms. And the average developer simply does not know how to build secure concurrent distributed systems. It's just complex enough as it is. Now throw 8 processors on them and they're just going to go ape. The next level of problem as we move up this ladder is the problem of design. Most interesting systems that work generally are stolen from systems that worked in the first place. And this is part of what I'm trying to do in the looking at software architectures. What is the history of evolution of many of these? Because I find that within a particular domain or a niche, once the core architecture has been established and it's reached economic viability in that space, there's often very little variation from that point thereon, largely because it's good enough and the economic forces are such that it's impossible to change unless you blow up the business and start over again. This is probably why folks like Google are a little bit annoying, because they had it easy. They had no legacy to worry about. Now, it'll be fun to watch them in about 10 years when they finally grow up. In fact, I'll tell you the story I do now, and please don't take this wrong, but the way I characterize you guys versus IBM versus Google is this. IBM is a company that's gone through a near-death experience. During the 90s, IBM almost blew apart, and we've gone to the other side and we're stronger and wiser for it. You guys are going through a midlife crisis. That's the way I'd characterize it. That you're in a great place, and yet your management's changing out from you. You've sort of lost a little of the buzz, and you sort of wonder, man, should I have gotten that sports car, or those kind of things. What do I do next? Google is a company that needs adult supervision. Is the way I'd characterize it. That if I were a 20-something with a dog and a futon, they'd be a fun place to work. But they're going to go through the same growth phase you have been, as well as IBM has been. So their problem is they're just making too much money, and it hides a lot of the evils that are going on there. Again, that's my opinion on IBM's. So for many systems then, we know how to build them largely because we built them before. This is why I am so enamored of the work that's gone on in design patterns. I would claim that in the last 10 years or so, the most important development in software engineering has been the ideas of design patterns and patterns that are higher than that, because they give us an opportunity, a language of expression that transcends individual lines of code and individual classes. Indeed, as I go in and do these archaeological digs, I'll go in and spend time with the architects themselves, and they have the design patterns in their head, but most of them don't have the language of design patterns. So they will say, I've done this and this, and I'll say, oh, it's this kind of pattern. And they'll say, well, I've never heard it like that, but that's what it is. So many of these patterns are part of their tribal memory, and they're simply unnamed. And therefore, part of the archaeological digging process is to give name to these things that they already have. And that's valuable because insofar as we can name these things, then the people that go on beyond them will be able to continue to grow that system in ways that fit the intellectual integrity of the original system. That's why if you look at the eBays and the Amazons and the E-Trades of the world, you will see distinct phases of for each of these, about 4 or 5 architectural epochs, in which they built something, it sort of reached its limits, they had to blow it apart and start over again. The first version of eBay, of course, was a whole bunch of I think it was PHP scripts, because the guy had a girlfriend and she wanted to sell her Pez dispensers online. So we whipped something together very quickly. That obviously wasn't going to scale. eBay today handles about what are they telling me, 1 million new auction items per day. And so this is an amazing system. Yet they're at a point where they can't blow it up anymore. They're at a point where they have a continuously running system that they can never turn off. And so they have a problem of architectural transformation, keeping this thing up and running and yet changing it out from under them. Now, with your operating systems and the like, you have the opportunity for, kind of controlling things, and you can kind of blow things up and start over, but there reaches a point of diminishing returns where you get tired and your customers get tired of things being blown up. The next level is more and more on the social side of things. I've got these systems of scale. How then do I organize my teams so that they can build these things? This is the problem of the social engineering of the teams themselves. It no longer is possible, even in the gaming world, to get a handful of people together and go build something wonderful and have a world-class operation. Just not going to happen. You may get to your IPO and then go on, but then the rest of the world's going to be unhappy with you. But to really build systems of enduring value requires a focus upon the organizations themselves. There's a delightful book by Jim Copleen and Harrison titled Organizational Patterns of Agile Development. And in it he takes a look at what hyper-productive teams tend to look like. How do they organize themselves in terms of their skill set? And I've seen the things that Jim has seen over and over again from a number of organizations. The next few I'm going to zip through because they're kind of technically interesting and they start addressing a lot of the human side of things. Barry Baim, in his work on costing models, and we don't, in my experience, we don't do a lot of formal costing models, but his Kokomo 2 work has a very interesting observation for me. He observes that the performance of any software project is a factor of these four main things: complexity raised to the power of process, time the teams, times the tools. The important thing here is that, and this is in the order of importance, that the greater the complexity of a system, the greater impact it's going to have upon its performance in a negative way. And furthermore, anything we can do to reduce complexity will have tremendous impact upon our performance. How do we do that? Well, the best way to reduce the risk of your software systems is to not write any software at all, obviously. And that's one of the things that's fueling a lot of the work in service-oriented architectures, because it means, in effect, it's message passing, for God's sake. It's the same kind of stuff, just through a different kind of medium, but it allows us to reuse systems in ways and at a granularity that we could not have in the past. It's also the case that a bad process can amplify complexity and a good process can dampen complexity. Let me skip over those. So, if you were to remember one thing from what I've said thus far, I hope it's this: that software development has been, it is, and it will remain fundamentally hard. And that's part of the excitement of being in this field, because it's not going to get any easier. The things that people are asking of us are more and more demanding, and that complexity is simply not going to go away. That being said, there are some things that we are pretty certain we know, and some things we think we know, and some things that we know we don't know. It sounds a little like Rumsfeld, but frightening. But here's some things that I think we know we know. In the end, the fundamentals never go out of style. That in the heat of battle, you may throw some of these things out. You've got to get a particular release out. You've got to do it. But insofar as your process allows you to go back and spend some time on these fundamentals to make things simpler, to go off and refactor, then you're going to be in the right place. What are those fundamentals? Focusing upon crisp abstractions, having a good separation of concerns, having a balanced distribution of responsibilities. In effect, having beautiful software. There is always economic value in so doing in the long term, although it may not be so in the short term. And the fourth one is not on this list, but I see among 2 or 3 really productive organizations around the world. And that's a focus upon simplicity. I've run across a few projects where literally, and I'm not talking Google here, I'm talking some others in the Valley, where they will spend about 10% of their development budget to intentionally go off and refactor and simplify from release to release. Their development staff has convinced their highest levels of management that there is tremendous economic value in so doing, and they've got a really good long-term process, a long-term perspective. Some things we pretty much know we know. Reuse, in my mind, is kind of a solved problem, in the sense that reuse of individual lines of code has proven itself to be economically uninteresting. It's practical, but interesting, but it doesn't have much impact, so I don't care about that much anymore. It's really reuse at the level of design patterns and up that we see economically interesting reuse, and reuse of systems as a whole. And this may be a little bit controversial, but I would claim also that I'm seeing a plateau in languages. And that if you take a look at most of the interesting language research going on, we're polishing doorknobs and we're doing some interesting things to make certain parts of it easier, but by and large I don't see any state changes in what language stuff is doing right now. Now, I think there are some opportunities, especially in the area of concurrency, in the areas of verification, as we talked about with some of your folks today. The latter is a little bit more polishing as opposed to being a fundamental shift, but I think that we're ripe for some fundamental shifts dealing with truly concurrent kind of languages. Now, a couple of things here before I open it up for questions. So I wanted to spend a little bit of time on the architecture project I'm up to. There are things like TOGAF and DODAF and MODAF and the Zachman framework and a whole bunch of things where people have said, if I want to describe a systems architecture, here's how I do it. When I first approached the Computer History Museum and said, you ought to do this software stuff, they said, oh, we already have a museum quality display showing software architecture. I said, love to see it. Happened to be one of Photoshop. And so they had this beautiful display, this black onyx kind of thing, pictures of the developers, and the way they represented the software was they had a box of Photoshop. And I suggested to them politely, there's probably a little more you can do. and so how then can I expose the beauty of software so that others can see it? In civil engineering, we see the beauty of systems by the physically built thing itself, but we in our world, we don't have those kind of things, so we have to look on the inside. I've been mostly inspired by the work of Philippe Cruchten in his so-called 4+1 model view, which observes that if you want to look at the essence of a systems architecture, there are at least 5 views you need to take a look at. 2 of them are conceptual. They deal with the vocabulary of the problem space and control structures. 2 of them are physical. They deal with things like your component architecture and how those things are deployed around the world. And then what ties it all together are basically the use cases that run this kind of thing. So as I'm doing my archaeological digs, in effect, I am creating an instance of this for every one of the systems I look at. Some people collect stamps, I collect architectures. So if you go to my site, and there's the URL for it there, I've collected about, well, getting close to 200 different architectures of different systems. Now, a caveat to offer here. These are diagrams written by the architects themselves, and they represent only one particular view of a systems architecture. So this happens to be the architecture of the Canadian Air Traffic Control System. I was involved with Hughes when they bid against IBM for the US air traffic control system. IBM eventually won it, and this is a great example in looking at what the FAA and IBM did about how really to spend a few $1 billion and screw up. It was just a disaster in so many ways. I remember being introduced to the project early on after they'd won the bid, and they say, oh, we're so proud we won this, and we're so happy we built these 2 new buildings, this one for our analysts and this one for our developers. And I suggested that was really a stupid thing to do. And you could just see the memo wars that were going to go on from there. Hughes lost that bid, and they went up to Canada and won it. And they were actually successful to the point where they're actually trying to sell this back to the US and other places around the world. And I think one of the reasons they were successful is because they had basically a team of 2 architects who were in charge of the intellectual integrity of the system. They built this thing in an incremental and iterative way. Now, this is a really crappy architecture diagram because it just says, well, it's a bunch of boxes and it's layered. Well, that doesn't tell me much. The real beauty of this comes in when you begin to look at the patterns that animate it. And that's why pattern languages are so important to me. One of the patterns that come out of this, if you study the architecture, is that they've got this notion of a mobile object. So I've got this object called a flight, which is an isomorphic with the physical flight itself. And as that physical aircraft moves from place to place, the software object also moves from air traffic control center to center. It has the nice side effect that if an air traffic control center goes down for whatever reason, there are automatic ways of replicating that state so it goes elsewhere and it never disappears. So in order to understand the Canadian air traffic control system, you don't have to just understand the structure, which is uninteresting. You have to understand the dynamics of the patterns that lie within it. This is the architecture of a future combat system being built for the Army, and it's sort of your classic, kind of, well, how would I describe this? It's a classic command and control architecture, but they made the design decision to put a bus in the middle, a message bus. They chose Corba, which in retrospect was probably a profoundly stupid thing, but the reason they chose a bus and all is that in their domain, you've got all these things on the outside and people shoot at you and blow them up. And so things come and go, which is really a mess. And so what can you do to build a relatively survivable system? And the answer is you have a bus upon which that works. Of course, you now change the single point of failure, but you can deal with that in other ways. If you look at the history of games, they've changed radically over the years. This comes from an ACM article. If you look at some of the games from around 94 or so, remember we had very, very limited computational resources, so most of the software was basically serving up polygons to some graphic processor, and you had very few cycles for AI or things like that. Next generation up, well, it's more complex, therefore it must be more interesting. But we now have the computational cycles to go off and do some componentization of these systems. In fact, it's to the point where you had third parties come in and they were able to build components for you. You can go to havoc.com, buy a physics engine. You can buy terrain mapping engines, all sorts of things that reduces the cost of entry for many of these organizations. It's amazing what you can do in learning about architectures by studying patents and papers. So one of Larry's early papers was written while he was at Stanford on the architecture of what was to become Google. And this is a curious diagram because it's a combination of both software and hardware. The barrels are obviously the individual servers. The ellipse-like things are mostly the software pieces. And if you look at Google's architecture today, it hasn't changed a whole heck of a lot, except insofar there are about 10,000 or more of these at each one of the sites. I think if you take an infrared map of the world and look for the hotspots, that's where you find the Google server sites, which is why they're building the next ones by rivers and the like. Google actually has a very simplifying assumption they can make, which is there's no such thing as a perfect search. There's a good enough search, and they'll assume that if you don't quite like the search, you'll just try it again and refine it. And so that's what simplified their problem for them. Compare that to the problem that an eBay might have or a Visa might have, where you can't have an imprecise answer. You have to have a very precise answer. And that means that this architecture is not certainly suitable to those kinds of domains. This is the architecture of the Pathfinder up on Mars right now. And what's interesting about this, well, let's see, the boxes are hardware, the ellipse shapes are software. What's interesting about this one, it's more of a network kind of architecture than what you saw in the layered architectures elsewhere. In fact, the real core of this comes into the design patterns behind it. If you look at the control structures for this system, it is a time-driven control structure as opposed to an event-driven structure. Here's how a typical mission will work. I'm up there on Mars, I've got these stereoscopic cameras, and on a daily basis the rover is positioned such that it'll send an image of all that it sees around there, and they're downloaded at the rate of about 10 baud. I mean, you're a long way away. And basically it's like having a cell phone on Mars and listening to that signal. It's a little bit noisy. So you get these pictures. Somebody on the ground then says, wow, that's a really interesting purple thing over there with antennas. Let's go to it. And so what they'll then do, the mission controller will then say, all right, rover, I want you to go there. And that's all it has to do, because the rover then has enough intelligence on board to be able to plot a path from where it is to that point, hopefully without falling into a hole or hitting a rock. And so it's semi-autonomous navigation in that regard. And the way its control structures are built are that you divide the world up into time, and certain things happen within one frame, and other things in another frame, and other things in another frame. And if there's an overrun, then you simply slip it to the next frame in this notion of subframes. So there is more predictability in what happens than what I get in, say, a web-centric system. And I don't want to talk about these. Okay, last thing I'm going to mention. Here's sort of the current state that I see the world in. The average application is continuously evolving, meaning we can never really shut it off again. The average interesting one tends to be connected, distributed, concurrent, has to be multilingual and multi-platform, has to be secure, has to be relatively autonomic. And most systems actually these days are not just individual systems, but they're more so systems of systems. This is why messaging kind of architectures are dominating again. And I say again because these are not new things by any means. Service-oriented architectures is just message passing recast in a different kind of mechanism. But ultimately it gets back to message passing itself. That's a typical system. Where I see us going, and I think I'm wildly off here in terms of the decades, that the coming decades are one of increasing transparency, What I mean by that is we are building systems that increasingly are finding themselves in the interstitial spaces of the world. And so we're building stuff that more and more people who care nothing about software are going to be using. And that's an incredible responsibility for us. The next generation, I think, is a time of total dependence. For us as people working in this civilization, the idea of being in a place where I have no software that's touching me will be utterly inconceivable, and it'll be hard to get away from non-software places. You'll probably see, resorts where people say, "Oh, there's no software here. How exciting!" Totally retro. And the decade beyond that, I would call one of the rise of the machines, and not sort of in the big mainframe sense. But here's what telegraphs this for me. Look at Japan for a moment. Japan is a place where you have a curious demographic situation happening. The population is actually shrinking. There are fewer Japanese predicted than there were. And the skewing of the elderly Japanese is such that we have fewer younger Japanese folks to take care of the elderly. So how do you deal with that? Well, one way is why not have semi-autonomous things that can help those older folks climb stairs or be companions for them, pets that don't poop, that kind of thing. And so that's why Honda and Sony and, well, just about everybody, every one of the interesting companies inside Japan is spending a lot of money these days on humanoid-like robotics. And so I think we're going to, that's going to come into our society as well too. Just my prediction. Here's what frightens me the most. Well, not frightens, but excites me. No matter what prediction you can have for the future, however outlandish it might be, it all depends upon software that we have not yet written. Now, it may be software that you've written and your children are debugging, but there's still a lot of software out there to be written. And that's why I consider it to be an incredible privilege to be a software developer, because what we are doing bit by bit is changing the world. And yet at the same time, it is an incredible responsibility, because what we are doing is changing the world in very, very subtle ways. So there you have it. I have time for 25 minutes of questions. Sure, thank you. Yes, way in the back.
So as you've gone through these archaeology exercises, have you seen best practices around recording tribal knowledge?
I have. I have seen ways that are better than others.
Are you sure you want to shut down your computer now?
I thought she was going to answer it for me. Wow. So, where was I? I have seen better practices. Let me give you the range of practices that I've seen. At the best end, I have seen organizations that have discovered or realized that they have lost control of their architecture, so they're actually spending time with an archaeological dig to intentionally go off and document the architecture they have. I was recently with the CIO of the state of New Jersey, and they said they were frightened because if you look at the demographics of their development staff, they have a lot of really young people, they have a lot of old people, not old people, people who are near retirement age. And they are incredibly frightened that those people are going to retire and there's so much knowledge they have they'll be utterly lost. So they're contemplating such a project, and we're trying to advise them on so doing. Other practices I've seen, which is related to some of the collaboration stuff I've done, are simply the preservation of wikis that people have to force design discussions about certain things. Another thing I've seen, which sort of popped up in the Xerox PARC era, that still I see people do, a lot of stuff happens on whiteboards. Take a digital picture of those whiteboards and put it on a website for your project. So those kind of simple practices seem to work well. There's not a single organization I've encountered that does it really well yet, except the one that I mentioned that I know is doing some archaeological digs, and there maybe are 2 or 3 of those right now. Most of them still keep it in tribal memory, unfortunately.
And what do they choose to write down?
What do they choose to write down? The good ones tend to write down the following 3 sets of things. what are the major design decisions? What's the rationale for those design decisions so we don't go back over them again? And then lastly, the major design patterns that structure the system itself. If they've done that, then you probably extracted this 70% solution from those folks. And I find that I have to go back to the architects themselves to get this information. I was doing an archaeological dig for Eclipse. Reasonable thing to do. And as I studied the documentation, I realized there exists lots of detailed design documentation for certain specific nasty pieces of Eclipse. And at the other end of the spectrum, there are lots of PowerPoint slides. And there's nothing in between whatsoever. So in order to really understand the architecture, I've had to go to Eric Gamma and John Wigan and others to say, tell me what was in your head. And it's in their head, but we're already starting to see some degree of architectural degeneration because these guys are no longer on the Eclipse project, and there are people who are continuing to maintain Eclipse, and yet they don't have what's in John and Eric's head. So that's what I'm trying to capture for them. Those three things seem to be relevant. Now, if you go to my site, you'll also see that I have a meta model for the other stuff that I'm collecting. That in addition to those three things, I'm doing it against the 4+1 model view, so the patterns are very important. I'm also collecting a lot of the meta information, the team size, the team structure, the tools that were used, and the forces upon the system at the time. Because I'm convinced, and I don't have enough empirical evidence to suggest this, that certain kind of forces will warp you to a particular architecture versus another. And I want to document the way it was, because if I relax a certain force, then that may lead me to change my architecture in certain ways. And so I'm simply trying to collect that as well. Great question. Yes?
I've heard it said in some papers in the past that software is different. And looking at the complexity of physical systems, do you think that's true, or is that, and no offense to the others here, it seems to be an excuse for lazy engineering in some cases?
Well, in fact, you know, how would I say this? We as an industry we've been enablers in the sense that we have kept increasing the computational resources at people's disposal. We've allowed developers to become sloppy because they're simply not constrained by things. I did a post on my blog recently about the coming constraints of heat and power, that most of us, as we think about scaling up stuff, we don't think about the cost of energy for our devices, and yet that's starting to become a force that weighs upon us, which requires us to become less sloppy. So, to go back to your initial issue, which I actually forgot, was a really fascinating one though. Is software different? And the answer I would offer is yes, it is, because physical systems, unless you're at the quantum level, tend to be continuous, whereas software systems are not necessarily continuous. And there is this explosion of state combinations such that a minor change in one place may cause a discontinuous behavior in another that I simply can't model at all. So that's why I think software is different in that sense, and which makes it so much more difficult for us. What do you think? Who knows? I think it is difficult. And also, not just because of that, but just because of the sheer size of the things we have to worry about. We are outstripping our ability to know how to manage developments that involve tens of millions of lines of code. And that's becoming a typical number for many economically interesting systems. We just are beyond our blocking and tackling there. Yes, way in the back.
So given your background, sort of irrational and so forth, and what you're learning through these archaeological digs, what role do you see tooling play in terms of what we were thinking it would do 5 years ago versus what you think it will do now based on what you're learning from looking at how these systems were designed?
So let me replay that back. What you're asking me is, knowing what I know now, what do I think this is going to do for us 5 or so years from now? Wow.
And how your thinking has changed based on
Oh, how my thinking has changed.
Archaeological digs.
Got it. Yeah, my thinking has changed quite a bit because, you know, there was a time in my youth where I thought áthe was the way God intended us to program. And actually, you know, I think perhaps there are many shifts, but I think one of the biggest shifts I've had in the recent years is that the problem is no longer one of language. but it's an issue of design and organization. Those are the two places that kill most projects in their success. And so this is maybe why the whole language area has reached some degree of plateau, that there may be some interesting things, there may be some breakthroughs. I don't see them happening immediately. I don't see any places for that, because the real hard problems are at levels far above languages. And that's been a shift in my thinking, that I thought it was more of a language issue, and I think it's not as much as it was. I've been disappointed in the whole modeling side of things. I'm disappointed in, this is my personal opinion, not that of anybody else, but I've been disappointed somewhat in the direction UML2 has headed, because there have been a number of folks that wanted to turn the UML into a programming language, which I thought was really stupid. And I always envision the UML and any modeling language for that matter to simply be a language to reason about systems. So I tend to use a very lightweight part of the UML. I use maybe 20% of it, and that's good enough for me to capture what I want to do in an architectural perspective. Anything else is a level of precision where the cost of that level of precision overwhelms the value of it. So that's another thing I've learned, that we maybe outreached ourselves on the modeling side. Not to say that modeling is unimportant. The other thing I think I've learned in this process is probably how much we don't know. My gosh, it frightens me to see the systems we built, and I go into places where these companies are my absolute heroes. They built some wonderful things. I go inside and I realize, wow, this is pretty butt ugly stuff you've built. And it's amazing that it still runs and works. And so the level of immaturity of many of these large systems absolutely has blown me away. Truly has. That frightens me somewhat. Good questions. Yes, there was a question up here.
You said that you are essentially a bit skeptical about the issue of the influence of languages, but on
yes.
the other hand, you also said that so many architectures, so many patterns of systems is actually just in the head.
Yes.
So in a way, what do you suggest here? Having more research on languages concerning patterns, or what kind of representation of architectures and patterns do you foresee?
See, I think that's one of the areas of unknown, and an unknown area, and an area where we can do continuing innovation. If you look at the work that the folks at CMU have done and the SEI have done, and others in the world in terms of architectural representation, we don't have any, there are some good ideas, but nothing's really caught hold entirely. We have things like the UML, we have various kinds of frameworks that allow people to describe architectures, but I'm not sure we as a community have looked at enough different architectures and simply tried to describe them to know if we have the right languages for them yet. And I'm not talking necessarily purely textual languages or purely graphical languages, but I think something that works at a level of abstraction that's appropriate for a system. Now I'm using UML, I'm using the 4+1 model view because it appears to be adequate for the systems I've looked at thus far. I honestly don't know if it's going to scale to systems of systems. I'm looking at things like the federal government's Fedline Advantage system, which is the software used to handle the resolution of all bond trading in the world. And I'm kind of a little stymied as to whether or not I can represent that. And yet, people need to, because there are a bunch of architects trying to keep this thing alive. So I just don't know enough yet. I think one of the other things I learned is when we built models and built modeling languages, we had a bit of chutzpah and we said, well, we're going to devise the modeling language and we'll apply it to the world. Well, I think that's bad science, actually. That probably the right thing we should do, which is what I'm trying to make amends for right now, is to be a little bit more I guess inductive is the right word, looking at existing systems, trying to document them, and seeing what we can learn from those specifics and find the generalities. In the past, we've done a lot of generalities and applied them to specifics. So I'm doing penance and trying to do the reverse. So I think the short answer to your question is, I think there is work to be done in the language space, in the area of languages that model architectures. We just don't know enough how to do that. And the other place is languages to support massive intimate concurrency. What I mean by intimate concurrency is closely coupled processors on a single slab of silicon. We just don't have the right means of expression to help people do that well. And I don't know if it's a language, I don't know if it's patterns, I don't know if it's libraries, just don't know enough. In the meantime, we'll muddle through for the next generation and do stuff. Good question. Anything from this side? Yes, Wayne, over here.
So when you showed the architecture of this air traffic control system,
Yeah.
you said, well, this looks nice, but it doesn't really matter because what really matters is this behavior of objects
Yeah.
moving around. That's kind of indicative of an experience that I have. It's hard to describe behavior of systems, especially when they're non-continuous.
Yeah.
Is there something that you do about that in the archive, or any notations that people should use, could use, that I just haven't seen before, or is this just open?
I begin with the IEEE standard 1472, which gives me some approaches to representing architectures. Where that standard falls short is that it says different views are important, but it doesn't tell you what views there are. So that's why I've chosen then the 5 views that I talked about. And one of those views, the process view, is where I capture control structure kinds of things, and I do so in the form of patterns. So if you go to my site, you'll learn that I've cataloged about 2,000 design patterns that people have already documented in the literature. So as I do these digs, what I'm trying to do is to say, well, the architects describe this, but boy, it smells an awful lot like this pattern, and so I'm trying to at least name those things. In other cases, I will discover they have a pattern that simply nobody has documented before. So for each one of the systems I'm documenting, for like the process view, I will have a basic description of what the control flows are, the task and process kinds of decisions, but then also an enumeration of the design patterns that animate that part of the system. And that's basically what I'm trying to document. Now that assumes that you know what those design patterns are, because if you don't, then it's not going to help you understand the architecture. But my gut says that across the 100 systems I've looked at, which is really the whole spectrum of many kinds of computable systems, there are probably 24 different, truly different architectures that exist out there. I don't think there are any more than that. And I hope in the end to be able to name those kinds of things. So there's work to be done, but I think it does come back to the notion of capturing the design patterns.
So in a sense, behavior is represented as structure? Because
well, remember, design patterns have both a structural as well as a behavioral element to them, so that they'll have the structure of the society of classes that interact with one another, but then also some specification of the temporal, complete, or partial ordering of their interaction. So that's why it's wrapped up in design patterns for me. Somebody in the middle. Yes?
So first off, it's just a blast for you to be here. And I always appreciate getting perspectives on people that have been in the industry for a long time.
Yeah. In other words, I'm old, yes.
Okay, but we have an industry that tends to burn people out at a young age.
Yes.
And so we kind of are like, we don't have the wise old men to say, oh yeah, I saw it 30 years ago.
Yeah.
And so if you're working on a project where the information is in people's heads, and to take it to the next level, you need to get it written down. But we have this culture of, so people will keep things in their heads as kind of job security.
Right.
So, I mean, that's kind of a big elephant in the room, right?
It is.
How can you get something to move to the next level when there's almost like a maturity that, like you have to trust that you're not going to write everything down and then shift the work off to some other group.
Right. I don't have a good answer for you on that one. I wish I did. I hope that the work I'm doing with the Computer History Museum and the architecture work itself is a beginning step to change the culture that preserving this stuff is relevant. There will always be the societal things you described, that I actually have my value because of the knowledge that I uniquely have, and therefore my net worth is augmented by the fact people have to come to me. So there's both very realistic economic benefit as well as egotistical benefit from doing so. That's the nature of the human spirit. It's not going to change. Although, insofar as that is true of your senior architects, that's economically devastating for the business. It'll happen in the small. It's going to happen in the small for the generations that come, because that's the nature of human nature. but I hope we can change the culture, at least from the architectural perspective. Didn't also happen to be this way in civil engineering. If you study the works of Vitruvius and some of the really early architects, the same phenomena you described existed around then too. I mean, my gosh, consider some of the things that I've read among the Egyptian architects. The king would kill the architects because he was afraid that their knowledge would be spread out to other places. Now, I hope we don't quite get to that point. All right, all you people who develop Vista, line up. This would be a very bad thing. So it was actually worse back then, and you know, we kind of got over that to the point now where we actually celebrate the architects of buildings. There's a book coming out from Tim O'Reilly's series called Beautiful Code, in which they've gone off and actually talked to people, senior developers, and said, show me an example of some beautiful code and talk about it. So we're starting to change that culture of the celebration of the artifacts themselves. And I think that's a good thing. So, you know, human nature the way it is, that's going to happen. So we'll change it bit by bit. Maybe time for 2 more questions? You and
So what do you think about the intentional programming that people talk about?
Intentional programming. Well, I was actually hoping to visit Charles while I was out here. Charles wrote me, and he's in Europe now. I guess he's still getting used to gravity. But here's my personal opinion about it. And I'm going to expand that to talk to you about aspect-oriented programming as well. I thought the whole notion of where that community was headed a few years ago was really cool and fundamental. But the ALP community in particular, in my mind, really got just stuck in the weeds. That they're worried about programmatic transformations for things that were economically uninteresting. I wanted them to look at aspects like security as an aspect, and nobody seemed to be climbing up to that level. So I do believe that there are cross-cutting concerns that impact many interesting systems. I do believe that the aspect community has utterly failed to solve anything in that space. I think Charles and his company are doing some fascinating things. I wish him well. If I had $1 billion to go off and spend, it might be fun to start a company like that as well too. I don't know about its economic viability, largely because of the embedded, stuff that people already have. And so it's hard to say if the work he is doing will make a fundamental change. I don't know. I have a very similar opinion with semantic web stuff as well too. I've been on one of the W3C committees dealing with OWL and the like, and alas, there were a bunch of academics that sort of seemed to take over that work. And while this is cool that I can now represent any conceivable form of knowledge in any human or alien language or whatever, I keep telling them it's just software. And so I don't really want to be able to go to the nth possible level, get me something good enough. So I fear that that's been over-engineered somewhat. We'll see. Last question, and I may even have time for an answer. Yes? You're the man.
It's a fun talk, and to play along, I wonder, so I want to say something you may disagree.
I hate it when people agree with me. It gets really boring. So say something controversial, like there's spinach between your teeth or whatever. I don't know. Insult me. Do whatever. Yes, let's hear it.
Your statement that language reaching a plateau,
yes.
I think it's probably not really interesting, except for in the case of concurrency. I think it's maybe premature. So we don't know, at least I don't know, how to program things like robotic systems. And I think the sort of intimate concurrency, intimate parallelism you're mentioning,
yes.
is just one example of that. When we talk about physical systems, it
yes.
can go a lot more than the intimate parallelism.
Yes.
And I look at the high school students programming robots, so look at that programming interface. So asking myself, is it an abstraction interface, a language? And so maybe my disagreement is pointless. Really, what we don't know. So the language we have are good for solving the problems we know. Maybe what we don't know is what's going to be the problem that are interesting.
Right, which is why we're going to be busy and having fun for the next several generations, because there are a lot of things we know we don't know how to do, and we don't even know we don't know how to do. And we don't even know we don't know how to do. And all of a sudden I'm in a recursive loop here. You touched upon a couple of things, a number of things, but two I'd like to make mention of. On the robotic side, turns out that there are emerging some common architectures that we see there. I met with the Sony team that does their Asmo robot, and I was utterly surprised to discover that Asmo is built upon an open source framework that was the same open source framework used for the little Abio dog. And so there's amazing commonality there. The architecture that appears to be emerging in those semi-autonomous kinds of things is what Rodney Brooks speaks of as a subsumption architecture. And so we actually are beginning to see names for these kinds of things, and that's an encouraging sign. You talked about education at the high school level. I volunteered at our local high school a few times, largely because at the urgings of one of my godchildren, she pointed out this poor instructor is just so lost, and her students know so much more than she does. Please help her. I came in and it was absolutely, annoyed to discover that the students who thought they were experts, basically what they were able to do is they could put together some simple websites. They knew how to install the latest patches from you guys, and they could do some simple programming in Visual Basic or whatever. And they were very proud of this, as they should be. But none of them had really been exposed to beauty, scale, and ideas of building good abstractions. Now, all these folks in this particular class, they were so enamored about games, and they were so proud of the things they built. And I said, let's look at some real games. Turns out the source code for Doom is open source. So I downloaded it, and I said, let's do a walkthrough. They had never looked at real industrial source code. And their first reaction was, oh, it's so big. And their next reaction was, oh, it's so ugly in places. And the third reaction was, how do you really understand this? And so I think it was eye-opening for them to realize there are problems of scale and beauty that they haven't been exposed to at that level. Earlier this year, I had the pleasure of giving a keynote address at the ACM Conference for Computer Science Educators. And actually, I gave a variation of this one. And one of the questions I asked their the instructors were out there, how many of you have reading courses? And they had no idea what I was saying. Well, if you're going to study English Lit, you study all the literature of other great writers. How many of you study the other great software writers in the world? And nobody raised their hands. So I said, well, here's an idea. Why don't you go get some good code and have your students read it and critique it so they can get an idea of what's really out there and what's good and what's bad. So there's still a lot of work to be done. I think there are some noble people trying to do some good things. What scares me is that the number of high school students who are interested in programming still seems to be plummeting, especially the number of women who care about programming is plummeting. That's why what CMU is doing with a programming system called Alice looks really cool. So there's hope, but we need to inspire that generation that programming is fun, and we have a ways to go. Thank you all very much for having me.